This is a review of Johnson High School AP Released Question Set number 7. And the first one is on photoelectron spectroscopy, and you might remember that a PES, the very high energy, is used to extract the electrons and ultimately all the electrons from atoms. And you get a trace of the energy needed to extract versus the number of electrons, or relative number of electrons, and the PES looks like this. So we consider the simulated PES plot produced by the analysis of the atoms of a single element, and they give you all the peaks in the PES. These hash marks here represent a big break in the energy, which, as you see, is very broad. So they've put together really 3 lines of this, or they've kind of smushed together a big long PES. So what's the electron configuration of the element, and hence identify the element. All right, so using this plot, we suggest the electron configuration of the element and identify it. And the lowest energy, of course, would be used to get what electrons? Well, the valence electrons would cost the least energy to get off because they're a distance, the highest distance away from the nucleus, and the Coulombic attraction is the least of all of them. Remember, energy is plotted right to left, and that's why this arrow is where it is. So the smallest energy should be the easiest valence electron, the one at the highest energy level. And there are 2 peaks here. Probably you've got s electrons in this peak and p electron here. So that's the highest energy level. And this here, so this looks like third energy level. Since you've got 6 electrons coming off here at this much higher energy, that must be one of the core, or 6 of the core electrons, and what you have there are p electrons, if there's 6 of them. And it looks like these here at 12.1 are the s electrons in that inner shell, which is the second energy level. And then you've got 2 electrons here that are real hard to get off. That's almost certainly the 1s electrons. Now, if we count these up, 2 plus 2 plus 6 plus 2 plus 1, we get 13 electrons. This has to be aluminum that has an atomic number of 13. Which peak or peaks are likely to represent electrons most likely to be removed when the atoms form ions? By now you should be able to determine that and explain it. The easiest is the smallest energy to pull, and that's 0.58. There's one here, and then the next smallest is 1.1. This appears to be a metal, and if it's aluminum, we know it's a metal. And it's going to lose 1 electron from the P, from the 3p, and 2 electrons from the 3s. So, this appears to be a metal. Now, using your answers here, identify the most likely charge on an ion of this element. So how many electrons will it lose since it's a metal? And the answer is the 2 rightmost peaks here, 1.1 and 0.58, add up to 3 electrons. Therefore, the charge on the ion would be +3. Suggest a reason, considering atomic structure and Coulomb's law, for the huge jump in energy between the peak at 12.1 here and the peak at 150. So think about that. Write it down and answer if you haven't done so already, and then come back to the video. Well, you've got a more than 10-fold increase in energy needed to remove these negatively charged electrons here. And remember, we talked about this being first energy level. This is second energy level. That's due to the fact that the 1s shell is the closest energy level to the nucleus. The nucleus has 13 positively charged protons, and so at 150, those two electrons are just almost impossible to pull off. So you've got to really hit it with probably X radiation in order to get those two electrons in the 1s orbital away. Okay, now there goes some titration calculations. This is Unit 4. A solution of 0.1 molar hydrochloric and 0.1 molar sodium hydroxide are prepared. So we're looking at the reaction between them, an acid-base reaction. We have 25 milliliters of one of the solutions in a beaker. It's titrated with the other solution, and a pH electrode is used to obtain the data. And we can see here, as we add the second chemical, we see a gradual increase and then a big jump in the pH, and then it levels off. Now, you've done at least once in your life a titration kind of like this. What's the solution originally in the beaker? Is it the hydrochloric acid or the sodium hydroxide? And I've kind of given this away here if you know what an alkali is. A strong acid will give you the required pH of 1 at 0.1 molar. So this must be the HCl. Now they ask on the titration curve for you to circle the point that corresponds to the equivalence point. Remember, you're adding 0.1 molar sodium hydroxide to 25 milliliters 0.1 molar hydrochloric acid. So where is the equivalence point? Well, we've got a strong acid and a strong base, and the millimoles are equal. That's the equivalence point. The pH would have to be 7 when you're going strong, and so you are right there, smack in the middle of this S-curve. Now, how many moles of titrant have been added at the equivalence point? Remember, you have equal millimoles of acid and base. Well, millimoles of sodium hydroxide would be milliliters, 25, times millimoles per milliliter, 0.1, or 2.50 millimoles. And remember, the AP folks are very fine with you answering in millimoles and doing millimoles and milliliters for molarity. Okay, the same titration is performed again, this time using an indicator. Using the information in the table here, select the best indicator and explain your choice. If you haven't done this yet, turn the video off, write down a good sentence explaining your choice, and then turn it back on. Well, the indicator should flip. Remember, the equivalence point is here at a 7. It should flip just past the equivalence point so that one drop of the sodium hydroxide will give you a nice sharp color change. Alizarin yellow here changes between 10 and 12, which is just past the equivalence point. Remember, this is a huge increase here in pH, and you've seen it in the lab. With one drop, you can just jump like 4 or 5 pH points. So if these are the only other two choices, they're just lousy choices, because this pH range is way down here. And where is it going to? It's going to bleed here. It's going to fade here. And the methyl red between 4 and 6, well, it's completed its change before you get to the equivalence point. You don't want to do that. It would be very hard to read the end point of the reaction and therefore to guess where the equivalence point is. So alizarin yellow would be your best choice here. Frankly, as you know, we prefer phenolphthalein, but that's not one of your choices. Now on this grid, sketch the titration curve that would result if you turned it around. That is, you put the base in the beaker and added the acid from the titrating burette? Well, you're going to start on the other end of the pH scale. Strong base would start off at pH 13, and then the acid would reduce the pH. You'd have the equivalence point at the same point, so the inflection point of the curve would be here. And this is my hand drawing with a mouse, so you know that's just a lousy curve, but I bet I get my point with that. Now let's go to gas equilibrium. Here is the deterioration or decomposition of what I like to call pickle 5, because that's what my organic teacher called it. And you have a container with a piston, and you've got all three of these gases in it. The initial partial pressure of the pickle 5 is 0.2 atmospheres, PCl3 is 0.04, and the chlorine is 0.08. What they want to know is the Kp expression. Well, that's easy. Kp expression is your algebraic formula using the concentrations, or in this case pressures, of your one reactant and two products. Well, it's going to be this pressure times this pressure divided by that pressure. Now they want to know, given these initial partial pressures, how will the partial pressures of each species change to reach equilibrium, if they do at all? Well, you've got this is very small, this is very small, and this is relatively large. So Q is 0.04 times 0.08 divided by 0.2. That's 0.016. That is far smaller than 0.497 here. So Q is way less than K. If Q is less than K, the system must adjust to reduce reactants and increase products. So the partial pressures of both products will increase and the reactant partial pressure will decrease until equilibrium is established at a K of 0.497. Once the mixture reaches equilibrium, somebody pulls the plug, pulls the piston out, not all the way, but just increases the volume of the container and didn't lose any gas. What will occur in the partial pressure of the pickle 3 that is present, and justify your answer? Now, we know that if it was a multiple choice question, you'd immediately choose it would increase the partial pressures of both of these, because if you've increased the volume, you're going to reduce the pressure, and the only way you can compensate is by making more molecules. But you can't use that argument in an FRQ. You've got to argue always from Q and K. So if you increase the volume of all gases, Boyle's law says all pressures will be reduced, and the pressure of the PCl3 will decrease. Okay? That's before any equilibrium is reestablished. But this reduces the numerator of Q, this, because of the product here, more than the denominator. So Q now is below K. That'll tell you what direction that it will go, and that naturally it'll go to the right. But I'm telling you, don't write that last sentence if all they're asking is what change will occur in the partial pressure of the pickle 3. That's not the question. That's the question they ask, so just answer that question. Identify the species. Now, identify the species that will be present in the highest amount at 200 degrees and justify it. Well, at that temperature, the reactant PCl5 predominates because K now is less than 1. The products must each be less than their reactant. Now, is this endothermic or exothermic? Well, if you increase the temperature, it increases K. That means products are formed and reactants are used up. Heat is acting as a reactant, so the reaction must be endothermic. And as PCl5 decomposes, energy must be used to make that happen. Energy is taken from the surroundings, so the temperature of the surroundings will decrease.